So let me remind you what we're trying to do. So we have the Heisenberg invariant. So we have the Heisenberg multiplication. And the Heisenberg multiplication, well, really this is the multiplication. I'm kind of confusing matters. This is the generating function of the multiplication after you've identified the Heisenberg algebra with a polynomial algebra. But I'm making shortcuts and I'm just calling it Mijk. And it's this function. It's the exponential of, well, what's written here. Greek and Latin letters. Similarly, we've computed we have the Heisenberg R element, and it is given by the exponential of uppercase T minus 1, so uppercase T was e to the lowercase t, minus 1 times pi minus pj times xj, and that's it. And in fact, there was also a C element, but I'm not writing it because there's nothing interesting to say about it at the moment. And what I want to do today is to see if I can perturb R. So instead of R, I want to switch to R epsilon. So R that will depend on a new parameter epsilon, which I suppose means that we allow everything is now allowed to be a power series in epsilon. So whenever I write something, whatever the scalars were before, now they're allowed to be power series in epsilon. And I want the perturbation term to therefore be a power series in epsilon. So I want to write it as a sum as k is greater than 0 of epsilon to the k times R number k, okay? This k and that k have nothing to do with each other, sorry. Okay. And I remind you what is the composition law. So the composition law of two generating functions is, so if you have a generating function L and M with Greeks A and Latins B and Greeks B and Latins C, the composition is, one way to write the composition is to multiply them, apply this infinite order differential operator, and substitute zeta and z is equal to 0. Oh, wait, sorry. I went too fast. Here, I want to say two things. First of all, what is Rk? So if I want to perturb, I want to find these coefficients, R up k, okay? And even before that, so you see, if R up k is allowed to be an arbitrary polynomial or power series or polynomial in the variables that I'm allowed to use, so the x's and the p's, then the space in which Rk lives will be infinite dimensional, and then I'll have very hard time solving for it or finding it. So even before what is Rk, I want to see if I can I limit the search? So can I restrict my attention to a smaller subset of Rk's? And the answer is going to be yes, and just as a preview, I'm going to limit the search to Rk's that are balanced and docile, and the space of such Rk's is relatively small, and therefore we will be able to find Rk. Okay. Anyway, you know, maybe also before continuing, I have a lot to say, but before continuing, maybe I want to give you a sort of how I see this equation written here and sort of what's happening below, okay? So basically, we have L, and we have M, and we want to compose them. And I'm thinking of them as I want to think of both of them, right? Because I'm going to need to compose such things. But so I want to think of both of them as perturbed Gaussians. What's my image of a perturbed Gaussian? So they have a scalar part, a coefficient part, then they have a quadratic part, and the quadratic part is made of a Greek part, a Latin part, a Greek-Latin part, and this is true for both of them. And in fact, as I mentioned, these are all exponentiated, so these are really reservoir of lines. Okay? And now, so this is the same as what we had before. And now we are also allowed higher order terms, which are also exponentiated, right? We're allowing higher order terms, perturbations, that are dependent on some parameter epsilon, but they also get exponentiated. So schematically, higher order polynomials added here would be polynomials like this, okay? So some Greek letters, some Latin letters, and each such polynomial comes with a coefficient epsilon or epsilon squared, some power of epsilon, but no negative power of epsilon. And this would be true for both generating functions. So here I could have another higher degree polynomial, and again with some power of epsilon. And now, if I wanted to compose these using the kind of techniques that I already have, I'd have to look at, well, so composing means gluing the things here with the things here. And I'd have to look at diagrams that are getting more and more complicated. So basically, you know, maybe I could start here, connect to here, go to here, connect to here, go to here, connect to here, then connect to one of the perturbation terms. But the perturbation term itself has other legs which could be connected to other things. It gets more and more complicated. Yes?
Just to be clear, so you are talking about the composition, right? So I don't know how the element, the epsilon comes in. I thought the element, the epsilon has to do with the R perturbed.
So R is one of the things that get composed. So now everything is allowed to have power series in epsilon. So L could be a power series of epsilon, M could be a power series in epsilon. So I mean, really the difference is minor. The only thing is that the only thing is that yeah, everything now is allowed to depend on epsilon as well. That's the only big difference. Anyway, so this is quite complicated as it is. Okay? So, you know, really the composition law is you allow to connect these with lines to these, and it gets really, really, really complicated because you have you can get diagrams that are very, very, very complicated by connecting these pieces from both sides. So the first thing that I do to simplify is, in fact, use this rule here. Okay? So so basically, roughly speaking, what I do is, first of all, I multiply these two coupons. And when you multiply them, you know, one way of viewing it is to grab it from here and open like that. Okay, so I suppose, you know, if the two coupons are like that, redraw them like that. So the result is, so the first coupon has W1, the second one has W2. Here we have the quadratic part, which of course has several colors, several types. And here we have the quadratic part, which has several types. And here we have the perturbation part. And here we have the perturbation part. Okay, so I first multiply them. And then I glue this with that. But gluing this with that is really gluing it with a thing like that, where, again, every edge represents a reservoir of edges. And that's what's written here. This is a single quadratic, okay, which gets glued to the product of the previous two. And things are still complicated, but a little less. Because now I can simply combine these two, and multiplying them, and I get a single scalar, and these terms all combine. The sum of two, the product of two exponentials of quadratics is the exponential of a quadratic. So here I'll just get a thing like that. Likewise, again, the product of two exponentials of polynomials is an exponential of a polynomial. So I simply get an exponential of a polynomial here. And I need to pair it with this. Okay, with the exponential of a single line. And that is what's written here. Okay, and also, I may as well lose the distinction between Greek and Latin letters. So now, here I have a mixture of Greek and Latin letters at the bottom, a mixture of Greek and Latin letters at the top. At the top, it's the letters corresponding to A and C. At the bottom, it's the letters corresponding to B. But I may as well lose the distinction and simply have a single set of variables called B. So B is a single collection of variables. And I want to, and given a matrix F with entries corresponding to the variables, I want to know how to glue F against an expression E. And this is defined to be e to the 1/2 f uv du dv, where here there is an implicit summation of over the variables, and u and v both belong to the set of variables B. So I want to compute this, and then substitute zb equal to 0 so that it's a complete gluing. That's exactly the picture that's drawn here. Okay? And my technique is to say, let's do partial gluing. So let's glue, but without substituting z, all the z's are equal to 0. So this basically means that I glue, so I mean, basically if you do this, then this is complete gluing. And if you do that, then this is partial gluing. And what it means is that, so if this is something that could be coming from the top, then you are gluing some legs, but you're not substituting z is equal to 0, so some leg remains. So some polynomial in the variable z remains. In the zb's remain. So that's this, the partial glue. And what we found a while ago, that if you set z lambda to be the logarithm of gluing lambda f to e, so basically you multiply f by lambda to make it a power series in yet another variable lambda, then this thing satisfies the differential equation z0 is equal to e, so kind of this e to the e is what was called calligraphic e here, and then z0 satisfies is equal to e, and the derivative with respect to z lambda of z lambda satisfies the equation written here. Okay? And now the question is, well, solve it. Okay? So I'm going to solve it in 3 steps, by writing 3 lemmas. Okay? Or not really 3 steps. Well, you'll see, in 3 steps. So step 1 is basically I'm going to get rid of the linear terms. So you see, from the perspective of the variables in B, this term here is linear, right? I mean, it's quadratic in the variables in A, B, and C, but at this point I'm only gluing along B. So from the perspective of B, this is linear. Likewise, okay, in fact there is also, from the perspective of B, there are also constant terms, namely omega is a constant term, just the obvious constant term, but also the quadratics that depend only on A and C are in fact, from the perspective of B, they're constants. So I have constants, linear things, quadratic things, and higher order things. So let's order things in terms of complexity. So constant things need not even be discussed. There is nothing to glue, applying a differential operator to a constant, you just get 0. So the constant, so I mean, this is really an exponential of a differentiation. So it's applying, so basically it's gluing 0 or 1 or 2 or 3 copies of this f. And the only contribution is from gluing 0 f's, because there's just nothing to glue to if you're talking about constants. But if you glue 0 f's, you just do nothing. So the action on constants is to do nothing. So constants are way too easy, are trivial. As we will see in a moment, linear is easy. So basically, if you have just such terms, linear terms, there is only one thing they can be glued to, and then there is not much of iteration could happen. No iteration can happen. So quadratic. So like from our perspective, quadratic is this. So quadratic is hard but manageable. And we've basically managed it already, because we already know that you just need to, well, glue iterates, and then you get geometric series, and we've summed them. So So we will do all of these. Actually, the first one we will not even do because there's nothing to do, but we will do the first two. And after we're done with the first two, we will remain, the only thing that will remain will be to glue a higher order polynomial to a quadratic. And that's, first of all, exactly the same as Feynman diagrams. And secondly, remember that these come with powers of epsilon. So, so basically, only finitely many of the, if you restrict your attention to some finite power of epsilon, like if you want to look up to epsilon to the 7, then at most 7 such vertices may occur. So you end up looking at a finite process. So maybe it's complicated, but at least it's finite. Okay, so the higher order is complicated but terminates. Okay, so now let's do that. So lemma 1, so okay, you know what, really there should be lemma 0, and lemma 0 is that there's nothing to do about constants. You don't need to say anything. You know what? Let me say it because I should have said. You know, what do I mean by lemma? What do I mean by trivial? So I mean that if you do the gluing against f of an expression e, and the expression e gets multiplied by some scalar omega, so omega is independent of the variables, so d omega to dzb for every element to dzi, for every I inside b is equal to 0. So no, it's not, does not depend, it's a constant. Then this is omega times gluing f to e. Okay, that's what, okay. So lemma 0 has been stated. Now let's do lemma 1. So lemma 1. So, wait. I don't know why, but in my notes I wrote lemma, well, okay, it doesn't matter. So, lemma 1, suppose you want to glue f against an expression e, which is multiplied by the exponential of something linear. So it's multiplied by the exponential of sum of yi zi, where the zi's are the variables we glue, as usual, and the yi's are the coefficient of zi. Well, if it's linear, it comes with a coefficient. And the so the yi's in principle are, well, in principle are also variables, but they're the variables coming from A and C. So from the Greek letters that are not involved in the composition, and from the Latin letters that are not involved in the composition. Okay. So, well, let's prove the lemma and then state it. Okay? So, what does this look like graphically? So graphically, we are gluing things in E. So these are the things, the things in E. And, well, I wrote a higher order thing, but it could be in itself quadratic. I mean, I wrote it as a degree 4 thing, but it could also be degree 2. Anything but linear. Okay? And I have the linear things. The linear things are, I write them as sticks. What I mean by a stick is that at this side I have a variable z, and it comes with a coefficient y. And now I want to glue this against f. What things can, and remember the rules, each of these is really a reservoir of things. So I could use as many f's as I want. This is also exponentiated, so I could use as many as I want. The e, the way I wrote it, is already the exponential. I didn't, so, but basically because it doesn't matter. So anyway, what can I get? So if I glue this, what can I get? So basically, every, sorry, every, so okay, the f's can be glued either to two sticks, so you will be getting things that have things that look like this. So f, and it's glued on both ends to a stick, so it's an f between one y and another y. Or a leg from E could be glued to an F, and then the other side of this F could be glued to a Y. So you'll be getting pictures like this. So maybe there will be another one. So I don't know. This might also be glued to a Y. And then the last thing is that the two sides of an F could be glued directly to E. So you'd be getting a gluing like this. So that's all the things that you can get. How do I turn it into a formula? So turning it into a formula, so these things together make e to the 1/2 Fij yi. You know, maybe I should have used upper indices here to make the summation more apparent. Yi, yj. Right, this is just f with the z's replaced by the corresponding by y's. So, so this is this. And what's that? So this is, first of all, you take E, then you do the substitution. So every z variable in E could either remain free, so before I glued these it was free, so either it would remain itself, or it could be replaced by a y with a coefficient f. So basically take E and substitute zi goes to zi plus really the sum over all j's fij yj. So remember, so I mean, if this was a z1, it could be connected to a y7, but then the coefficient would be F17. Okay? Now, after you do this, oi, I did it wrong. Well, after you do this, the z's that remain free must be glued with f's. So, really, I should have written here f colon, yes. So, what have we achieved? So, if we wanted to contract an f with an expression that had a linear term, well, we could take this expression, apply a substitution to it, but it still has no linear terms. It now has no linear terms because, well, I've isolated the linear term, and if you make this substitution to, wait. No, in fact, it still may have linear terms because after the substitution, you will have new linear terms. So what have I achieved? What I have achieved was different. It's not that I've gotten rid of the linear terms. There might still be linear terms, but I am thinking of E, calligraphic E, as coming from a perturbation. So, so it's in principle. Well, so it's the exponential of something proportional to epsilon. And now, and I've isolated away the part that's not proportional to epsilon. So now everything here is proportional to epsilon. So there is only it's only finitely many iterations that might be needed.
Yes, a question.
Yes.
Quick question. Could you explain what the y again? The linear part. I don't really get it. Why you have double y's when you pair it with f?
Okay. You know, let me say one more word. I'll get back to what you said, but one more word. Sorry. Now I realize why in my notes I've done the lemmas in the opposite order because. Really, lemma 2 really does get rid of the quadratic term. Anyway, no, it's actually subject again to the same issue. Okay, you know what? We'll get to lemma 2 in a minute. So again, So again, I'm gluing linear terms and complicated terms to a quadratic. And again, everything gets exponentiated. So really, this really stands for e to the f 1/2 uv du dv, and this is really e to the z. So this really stands for e to the yi, zi, and this is some polynomial in the z's. Okay? So again, when I'm gluing z's to z's, in other words, when these differentiations act on these z's, there are three possibilities. One possibility is both of these derivatives act on a z coming from a linear term. So, and that gives you a picture like this. Okay, so basically, I'm not sure what to say. I mean, if you, so you know, let's let's write it like this. So if you have f(2,7), sorry, it's not 27, it's 2,7, d to d z2, d to d z7, acting on e to the lots of things, but these lots of things include y2 z2 plus y7 z7. So what's this equal to? So the d to d7, d to d z7 acts on the z7, and the coefficient y7 drops out. So you get y7 times the same exponential. And then you differentiate with respect to z2. So this pulls down a y2. So you get y2 times the same exponent, sorry, y up to, times the same exponential. So write every pair of differentiations like this, and it comes with coefficient f(2,7). Okay? And in fact, the 1/2 drops because, no, it doesn't drop. Sorry, it doesn't drop, it just stays. Sorry. So every time you apply the Laplacian, so this expression that gets exponentiated here, every time you apply it to this exponential, it pulls down an f(2,7), y2, y7, but of course this is sort of 2 and 7 are I and j, and you sum over them, so you get a summation. So you get this. Okay. Now this is only from the contributions where the f acts on the z's, on the struts, on the linear terms, where both sides of f act on the linear term. But then there are two other types of contributions. The types where one side of f acts on e, and the other side acts on a linear term. And these actually end up implementing the substitution. And then the terms where both sides of f act on what remains from e. And then that's the final gluing here. I'm sorry, these things somehow became second nature to me. Like, this is how you do algebra with differentiations. Okay, you don't, I don't know, you don't apply Leibniz's rule. You think where the derivative acts. Okay, and so there is some pictorial language, and I think I'm trying to connect you with the pictorial language, but I'm having well, I don't know, you have to get used to it. So, I mean, in fact, to somebody who knows the pictorial language, I'm done with the proof. I mean, that was a proof. I've enumerated all the possibilities, and they all correspond to algebraic things here, and that's a proof. If you're comfortable with the algebraic language, with the dictionary between algebra and pictures. If you're not comfortable, then you can spend a long time working hard, and you could derive it from, say, this equation. So basically, you will throw in a lambda in front of f. You will assume that this thing satisfies the synthesis equation, and then you will show that the left-hand side satisfies the synthesis equation by differentiating and verifying. So, I mean, you could give a fully algebraic proof, but I'm happier with the pictorial proof. Anyway, let me mention lemma 2. So lemma 2. And in fact, in my notes, it's lemma 1, and I'm not sure why. So f paired with some arbitrary expression multiplied by the exponential of a quadratic, so 1/2 Zij is equal to, so again, let's prove it and then write the result. So now the picture is, I am trying to glue an exponential and an exponential of a quadratic and an arbitrary polynomial. So this one is a g quadratic against an f quadratic. And what do we get? So there are two things that can arise. So one is, well, I could start from a leg of here, do an f, do a g, do another f, do another g, so do an arithmetic, a geometric series of f followed by g's. And then at the end, I'll end with the, I'll come out again with an f and connect it to another leg. So basically, I will get diagrams like, so my original diagram, and then zigzags that do f, g, f, g, so f, g, f, g, f, and these are unbalanced, so more f's than g's, because, well, you do f, then you do g, then you do an f to come back. So you do zigzags like this, okay? Including the possibility of doing only one zig, so so just one f, okay? So basically, you have to manage all the legs of E with this way. So this leg could be connected with this one again by a zigzag, okay? And then there is another term, and the other term, the other contribution is the contribution where where you get closed FG loops. So basically, one way to see it is to have a single G and a loop like this of F's, 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 G, G, and then the original G. And yeah, and you get the product of these two. So I mean, really, you get the exponential. So all of the so every possibility to do this times the exponential of that. Now, this we've computed. This, well, we computed it first intuitively, and then it actually followed from the differential equations we wrote. So this is just the determinant. So this is e to the trace of 1 over 1 minus so the sum of the geometric series. So 1 over 1 minus fg, or gf, it doesn't matter because trace is insensitive to order. And this is, sorry, and there was a 1/2 somewhere. Sorry, and there was a log also. I don't remember. It was something like this. And this became the determinant of 1 minus GF to the minus 1/2. So here we will get the determinant of 1 minus GF to the power negative 1/2 times, so this is this contribution. These are the closed loops. And what is this contribution? So this is really pairing the original E with the sum of the geometric series that you get by getting FG, 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 FG. So this is really times F times 1 minus GF inverse paired with E. So what have we achieved? Well, we've gotten rid of the quadratic. Here we've really gotten rid of the quadratic. So here there is a quadratic term, and here there isn't a quadratic term, and instead we're gluing with a different matrix. Namely, the matrix that you get by looking at all the sums, like all combinations, FG, 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 FG. So this is lemma 2, and again, the pictures prove it, and if you don't believe the pictures, you can reprove it by differentiation, by showing that it solves the same differential equation. And I'm out of time, but the next step is to do the higher order terms on the assumption that there are no quadratic and no linear terms. So it's a finite process, even if complicated. Okay, so see you on Wednesday. And so, yeah.